Hi everyone. Good morning.
Morning.
Yes, good morning. Yeah, so what was the last part that we have discussed? What did we study in the last session, guys? Uh, do you have any questions, everyone, in the last session? Okay, so I'll just share my screen and we can start with the next part. We'll start with the same worksheet itself. So this is 15th December. We have concluded linear regression and we are going to start with the new machine learning module, that is your logistic regression. So we have seen in the last session that linear regression model can be used to make predictions for continuous variable, right? Linear regression model can be used to make predictions for continuous variables, right? Now, in this module, you'll learn logistic regression, which is a classification model, and it will help you out to make predictions in cases where the output is a categorical variable. Logistic regression, which is a classification model, and it will help you make predictions in cases where the output is a categorical variable. Since logistic regression is most easily interpretable of all classification models, it is very commonly used in various industries such as banking, healthcare, and etc. So, what we are going to do is we are going to take one data set, a real world scenario, and we'll just try to understand why logistic regression is necessary or why there is a need of logistic regression, why linear regression fails, right? Now, in this session, we are going to discuss uh, univariate logistic regression, univariate logistic regression, and further we are going to learn few basic concepts related to logistic regression. Broadly speaking, the topics that we are going to cover in these sessions are binary classification, sigmoid function, likelihood function, building a logistic regression model in Python, and odds and log odds ratio, right? You learn about all these concepts through a univariate logistic regression example. And also, if this term sounds a little alien to you right now, you don't need to worry about. By the time you are done with this module, you will be well versed in the terms of odds and log odds ratio, right? So let us try to understand what do we mean by binary classification. What is a binary classification? So, examples of classification. First of all, what do you mean by classification? Whenever your target variable is categorical. Yes or no? Means you have categories like yes or no, true or false, or any other categories. Rather than numerical, when your target variable is categorical, let's say whether you are interested to predict a person will get loan or not, or whether you're interested to predict certain email is spam or not, right? So these are some examples of classifications. Finance company wants to know whether a customer is default or not. Predicting an email is spam or not, and categorizing email into promotional, personal, and official, right? So these are some examples that we are familiar about. Can you guys think about some other examples? Can you guys give me some other examples here? What can be examples of classification? Yes, everyone. What are the different examples of binary classification? Cancer detection. Okay. So there can be any examples, but you should be able to be in a position to frame out some examples, right? Now, coming towards the binary classification, uh, first point, it has only two possible outcomes. Then only it is known as binary classification, meaning that we can have only two output. I mean, your target variable can have only two possible output: yes or no, true or false, right? Or class 1 or class 0. It can be anything. It should be only two possible output. Second is you have examples. You Examples that we have discussed are whether a customer will default loan or not, or spam or not spam. That can be the examples of your logistic binary classification, right? And so now you know what a binary classification problem is. In the next uh, discussion, we are going to take specific examples and try to understand why linear regression is not effective in this kind of problems, right? So what I'll do is just I'll uh, create a dummy data. Suppose here we have blood sugar level, here we have diabetes. Blood sugar level, we have it as uh, 200, 150, 220, 234. So let's consider we have a data set, right? And we are going to work on the same data to fit the logistic regression model. But as of now, just consider we have this data and whether a customer has diabetes or not. So if we have, if the patient has diabetes, it is yes, it is one. If no, then 0. 1, 0, 1, 95, 0, 1, 1, 0, 0, 156, 0, 160, 1. So suppose you have this data, right? And what we are trying to do is we are trying to plot this data on your X and Y axis. So I'll just try to plot this data. So it can be anything. I just have taken random data set. So earlier, to just give you guys an idea, earlier this column was like this, yes or no. We have converted that into your numerical variable by doing the encoding or mapping, right? Now, what we are going to do is we'll plot this data. So let's say this is class 1, that is diabetes. This is class 0, no diabetes. And these are some data points. So we have this data 1, 2, 3, 4, 5. On x-axis, you have blood sugar level, let's say. And this is your 1, 2, 3, 4, 5. These are the data, right? And you can consider this is, let's say, 90, this is 150, 200, 300, right? Now, if you try to put a decision boundary by using a line, let's say linear regression. Suppose if I just draw a line, will it cover all the data points like it used to do for linear regression? Not all, basically, most of the data points, right? We can plot a line which will try to cover maximum data points, right? But here it is not possible. Suppose if I draw this line, then also not possible, this line not possible, this not possible, this not possible. So one of the reason why linear regression fails in this categorical or classification problem is this only. Like we cannot put a decision boundary to separate the data or to just classify the data, right? So one possible solution could be I can write down uh, this as a decision boundary, let's say. So on the left hand side of this decision boundary, I can say that this is class 0, and on the right hand side, whatever I have class 1, that is diabetes. So this is little bit correct solution, like putting a decision boundary like this. But still, if you see, if we have a data, these two data points, like for an example, this data and this data, they are misclassified, right? It says that on the right hand side it should be diabetes, but this has no diabetes, this data point, and this data point has diabetes, but it classified it as a no diabetes. Again, if we have a data like this, then what can you do? This one, this one, right? So that's why we should use logistic regression. So one very simple solution to this problem is to use a sigmoid function. What is a sigmoid function? One possible reason could be, possible solution is I can create a decision boundary like this, right? This, 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 right? So how do you convert your uh, solution into this kind of S-shaped curve? This is something like S-shaped curve, right? S-shaped curve. This is known as use of sigmoid curve or logistic function, right? So we use sigmoid function, sigmoid function. We'll see that. We'll discuss 5 to 10 minutes more about this sigmoid function only. This is also known as logit or logistic function. Logistic function. Logistic function. So both are the same. Its formula is like it's very simple. 1 divided by 1 plus e to the power minus x. And you can consider this 1 divided by 1 minus. And it it converts everything into S-shaped curve. So if you have a data, if you pass your data into, let's say, this sigmoid function, it will convert your data into S-shaped curve. So basically, all the data points range will lie from 0 to 1. It will convert it into probabilities, right? Now I'll remove this. I'll just, whatever I have drawn, I'll clear this. So if you just pass your data in this function, 1 divided by 1 plus e to the power minus x by using sigmoid function, you convert your data into 0 and 1 like this, and all the data points will be somewhere or somewhat closer to this sigmoid curve, right? Depending upon the values of this. So actual formula is 1 plus e to the power minus beta 0 plus beta 1 x. You can consider this beta 0, beta 1 x as this only, y is equals to mx plus c. So I can say m is equals to my beta 0. Sorry, c is equals to beta 0 and m is equals to beta 1, and this is x. So y is equals to mx plus c, right? Now this beta 0 and beta 1, we have to kind of manipulate, set the correct value of beta 0 and beta 1. We have to find that such that your this S-shaped curve will vary. So if we select, let's say beta 0 is equals to 5, beta 1 is equals to 10. So for an example, just hypothetical, I am getting this S-shaped curve, right? So if I try to maximize this to 8, minimize this to 8, so the shape is changing, right? And what we are trying to do is we are trying to fit a sigmoid function in such a way that we should able to fit all the near about all the data points that we have, right? So that is your sigmoid function for you. Now what we'll do is uh, we'll try to understand the sigmoid curve. So as I have told you, beta 0 and beta 1 concept. So suppose for a particular beta 0 value, that is minus 15, beta 1 equals to 0.065. I have this data point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have some this data point, right? Now here also I have this. So this y is equals to a probability formula, probability of diabetes, probability of person having diabetes is equals to 1 divided by 1 plus e to the power minus beta 0 plus beta 1 x, right? Now I'll show you one visualization from where you can understand uh, if we take different beta 0 and beta 1 value, how your sigmoid curve will change. So just give me a minute. I'll just show you that. Yeah, this is that visualization. I'll just share this. Okay. So if I just uh, try to change. Can you see here my beta 1 value, beta 0 value is -12, beta 1 is 0.05. I'm getting this curve, but my data points are here, right? This, and this. So I'll just try to change beta 0 value and beta 1 value. So my shape of the curve is changing, right? Can you see that? So that's what it is like. By changing beta 0 and beta 1 value, your shape of the curve, sigmoid curve is changing, right? So you have to minimize or maximize this logistic or sigmoid function based on some uh, based on these values beta 0 and beta 1, right? So you'll get best sigmoid curve. What is the best sigmoid curve? That is just like your best fit curve, which will be having uh, beta 0 and beta 1. And before you move on to that, here's an interactive what you can say app that you can try it out. I think this is but this is confidentially. You guys will not be able to access that. Anyway, that is fine. You guys have got an idea about that. Now, let's say this is our data. We'll try to find the best sigmoid curve. So now it's time to find the best sigmoid curve. Best. So for that, we'll just take one figure. Okay, so what the best sigmoid curve is? How do we find the best sigmoid? Okay, so let's say you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are my data points. Now, this is probability, like this is P1, this is P2, probability of uh, person having diabetes. And likewise, you can just try to draw, suppose this is P3, this one is P3, right? Now we are understanding very important concept. Then let's say this is P4, this is P5, this is P6, this is P7, P8, P9, and P10, right? These are my probabilities. Now, what we are trying to understand is, let us define this. P is probability of person having a diabetes, right? Our whole and entire purpose is to find the probability of person having diabetes, right? So this P1 that we have here is actually a probability of having no diabetes, right? Because this person is having not diabetes. So we whatever value we have over here, whether it's 0 0.1, 0.2, or it can be anything. That probability for P1, P2, P3, P4 is for person having no diabetes, right? So there are some data points over here, that is P1, P2. Uh, we have P3, we have P4, and let's call it as P6, right? So if you are taking from this line, that is your, this is origin, but we have a baseline or reference line. If you are taking a probability from this point to that line, or let's say from this point to that line, this line, that is your person having no diabetes, right? But if you're taking probability upwards, right, not downwards, upwards, from 0 to upwards, from 0 to upwards here, or from 0 to here, this the one, suppose this is P10, this is P9, this is P8, this is P7, and this is, let's say, P5. And I also have one point, that is P6. That point, 6 point, uh, is a point, or is a customer or a person that does not have diabetes, that do not have diabetes, right? So I'll just write down over here for your understanding. Like this P1, P2, P3, P4, P6, this the what we can say patient, they don't have diabetes. So we call it as no diabetes. And apart from that, whether it can be P5, P7, P8, P9, and P10, these are having diabetes, right? So we only have probabilities of no diabetes. These are whether it's P2, P1 to P6, and these are the probability of no diabetes, and this P5, P7, P8, P9, P10 are the probability of having diabetes. Now we are trying to understand very important function over here, that is known as likelihood function. Likelihood function. It is nothing but uh, it's a probability. We are finding probability of a person having diabetes, right? That is your likelihood function. So I'll just take this over here. Probability of a person having diabetes. We are trying to find that. And so the equation becomes, let's write down over here. So this is this probability P1, P2, P3, P4, P6 is of no diabetes, right? So if my no diabetes probability is 0.2, so what is your probability of having diabetes? It is 0.8. Yes or no? That is 1 minus 0.2. So P1 plus P2, or P1 plus 1 minus P1 is 1 only, because your probability of that particular point, sorry, this should be P1. Probability of P1 having no diabetes plus probability of P1 having diabetes is exactly equals to 1, right? So for an example, let's say let's call Abdul. Abdul probability of having no diabetes is 0.8. So what is Abdul's probability of having diabetes? It's 0.2. Yes or no? Are you guys understanding this point? Or probability of having diabetes is, let's say, 0.2. So what will be your probability of having no diabetes? That will be 0.8. So that's why here we are trying to find the maximum likelihood function. So we are checking probability of having diabetes. Even though this patient does not have diabetes, but for them, what will be the probability of having diabetes? It will be 1 minus P1, 1 minus P2, 1 minus P3, 1 minus P4, right? 1 minus P6. And already we have this probability of having diabetes for this patient. So we don't need to do 1 minus, right? So it will be again into probability of 5, that is diabetes, P7, P8, P9, P10, right? And this particular equation is known as likelihood function, right? This product is called as likelihood function. So the best combination of beta 0 and beta 1 will be, best combination of beta 0 and beta 1 will be the one which has maximum likelihood function, right? So we have to maximize this function in order to get best sigmoid curve. In order to get best sigmoid curve. So we have to maximize this, right? Now I'll just give you one activity, a very simple one. You have to create a likelihood function for this data set. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Let me minimize this little bit. Yeah. So 1 having no diabetes, no, no. Sorry, it should be here. 2 having no diabetes, 3 having no diabetes, 4 yes, 5 no, 6 yes, 7 no, 8 yes, 9 yes, and 10 yes. This is my thing. Now, what is your likelihood function would exactly equals to? What will be your likelihood function for this? So I'll give you 2 or 3 minutes. You can write down in the chat what will be your likelihood function for this. It's very simple. What will be your likelihood function for this? So we have to maximize this. That's why we call it as maximum likelihood function. Simple. So it is also known as maximum likelihood function. Now you have to write down this. So here 1, 2, 3, 5, 7, they don't have diabetes. So it will be 1 minus P1 product 1 minus P2, 1 minus P3, 1 minus P5, 1 minus P6 into P3, P4, P6, P8, and P9, P10, right? So this will be your likelihood function. We have to maximize this. This will be your likelihood function for this particular data point, right? Now it's time to find the best sigmoid curve. So how do you find the best fit sigmoid curve? How do you find the best fit sigmoid curve? In the previous lecture, you understood what a likelihood function is. To recap a likelihood function for our data, that is this, suppose this, the best fit sigmoid curve would be the one which maximizes this value of the product. So if you had to find beta 0 and beta 1 for the best sigmoid curve, you'd have to try a lot of combinations unless you arrive at the one which maximizes the likelihood. And this is similar to your linear regression beta 0 and beta 1. That is your M1 and C1. That will be a best fit line until you find the combination that minimizes the cost function in the linear regression, right? Now, to just give you guys an idea, like uh, what will be your best sigmoid curve? It will be the one which has, suppose this, let's take this figure, and actually this is also fine, no problem. Okay, so the I'll just write down points over here: 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, we want to try to maximize 1 minus P1. This is P1, right? 1 minus P1 will be above to that point. Means for probability 1, for point 1, what will be the, for point 1, what will be the value of person having diabetes? It will be this. For P2, what will be the probability of having diabetes? It will be this. Again, it will be this. For this, it will be this. But for this, it will be down. Again, this will be down. This will be again down. Because this is probability of person having diabetes, because this data points, this one, this one, this one, this one, this one, they have diabetes, right? So its probability will be this. But this point does not have diabetes. So their probability is upside above, right? Now, the best fit sigmoid curve will be the one which has the highest number of vertical lines. So the length should be maximum, right? So suppose I have this one, and again I have, let's say, this one. So in that, vertical lines are only 1, 2, 3, 4, and 5. Here we have 9 to 8. Here we have 5. So in very simple words, the best fit curve, just by looking at the curve here, you can get a general idea of the curve fit. So just look at this red line, red bars for each of the 10 points, and the curve which has a lot of red bars is a good curve. For example, for an example, this one. So this is, if you compare this with this, so this has 1, 2, 3, 4, 5. The red bars, yellow bars are very less. So here 1, 2, 3, 4, 5 only, right? But if you compare this with the other diagram, this has high number of yellow bars as compared to this. Yes or no, guys? So which is your best fit curve? This will be a best fit curve. For beta 0 minus 12, beta 1 0.056. So the curve which has high number of yellow bars, or the curve that has lot of big yellow bars, is a good curve. Simple. So you have to draw this and you have to find the best fit curve. And we have one more thing, like we have three, no, two only. Okay. This is, this one has 1, 2, 3 less big yellow bar. This one has high number of yellow bars. So this is your best fit curve, right? So clearly this curve is a better fit. It has many big yellow bars and even the small ones are reasonably large just by looking at the second curve that I have shown to you, right? So you can tell it will have high likelihood value. Simple. Yes or no? Now you guys can go through this. We'll take a break, short break. And after the break, we'll see odds and log odds ratio. Right? This is also very, very important point and very simple one. I'll explain this in very simple words. What is odd and log odds ratio? We'll see that. So it's 9:50. Let's have 10 minutes break. You just go through this, revise this, whatever we have discussed till now, and then we'll see this. All right. So what is odds and log odds ratio? So far we have understood that the probability of logistic regression P is given by 1 divided by 1 plus e to the power minus beta 0 plus beta 1 x, right? Now, recall that this equation gives a relationship between P, the probability of having diabetes, and the X, that is patient's blood sugar level. While the equation is correct, it is not very intuitive. In other words, the relationship between P and X is so complex that it is difficult to understand what kind of trend trend exists between the probability and X. It is very difficult to understand this, what kind of trend exists between them. So if you increase X by regular intervals of, let's say, 11.5, what will happen? So X, we increase it by 11.5, then again 11.5 plus 2x. Like that, if we increase our X with the regular interval of uh, 11.5, let's say what happens? How it will affect the probability of having diabetes? And will it also increase by some regular interval? We'll see that. What if not, what will happen, right? So clearly the relation between P and X is too complex to see any apparent trends. However, if we convert the equation to a slightly different form, to slightly different form, then you can achieve a much more intuitive relationship, that is what log is, right? So we'll just try to understand like why and how this log and odd logs term comes into the picture. So the probability of diabetes, which we have discussed, is 1 divided by 1 plus e to the power minus beta 0 beta 1 x. Now what we'll do is we'll just try to use some mathematical concepts. So 1 plus e to the power minus beta 0 plus beta 1 x, 1 minus p is equals to e to the power minus beta 0 plus beta 1 x divided by. So we are just using 1 minus p over here. Here also 1 plus e to the power minus beta 0 plus beta 1 x. Now, what you are doing is you are dividing these two terms, this equation 1 and this equation 2. So it will be p divided by 1 minus p, and this will be this will get cancelled. It will only come with uh, this is e to the power minus, right? It will go above. It will be e to the power beta 0 plus beta 1 x. And then we take log, that is natural log of p divided by 1 minus p, natural log of p divided by 1 minus p. Natural log of p divided by 1 minus p is equals to beta 0 plus beta 1, right? And this particular term is known as log odds. This is known as odds, right? So we are going to interpret this odds and log odds. So for an example, if this odds, now as we have discussed, p divided by 1 minus p is odd. So I'll write down over here, p divided by 1 minus p is odds, and natural log of p divided by 1 minus p is log odds, right? So for an example, this p divided by 1 minus p is your 4. That is your odds. So in other words, p is your probability of having diabetes, 1 minus p is your probability of having no diabetes. So I can write down probability of diabetes. This 1 minus p will go to the right hand side. It will become 4 times probability of having no diabetes. Yes or no? So it is 4 times, right? In other words, probability of having diabetes is 0.8. 1 divided by 4, no? Probability of having diabetes is, let's say, suppose if it is 0.8. So what will be the probability of having no diabetes, right? If probability of having diabetes is 0.8, probability of having, yeah, it will be 1 divided by 0.4 will be, 1 divided by 4 will be 4, 1, 2, so. Or let's say, let's consider probability as 0.5 first. Let's consider a different scenario. Just we'll take probability as 0.5. So I'll just remove this. Yeah, so we'll take probability is equals to 0.5 now. So 1 minus 5 becomes 1 minus 0.5, that is 1 minus p becomes also 0.5. So this ratio, p divided by 1 minus p, it will become, yes guys, it will become, it will become 1, right? So that is what it is, right? Now just you're trying to make balance, right? For an example, this is odds, right? So odds equals to 1. Now when we call it as odds is equals to 2, when will be the scenario when if your odds is equals to 2, what will be their probability? So let's try to solve this. P divided by 1 minus p is equals to 2. P is equals to 2 times 1 minus p. P will be equals to 2 minus 2p. P minus 2p is equals to 3. P is equals to 2. And p will be 2 by 3, that is 0.0067, right? So probability will be 0.67. Now, depending upon your odds ratio, you can find the probability very easily. Depending upon your probability, you can find your odds ratio, or depending upon your odds ratio, you can find probability very easily, right? So you can try to uh, play with this, and you can try to understand when it will be thrice. If the odds ratio is 3, so what will be a probability? So instead of probability, you have odds and log odds, and clearly the relationship between them and x is much more intuitive, and it is easy to understand, right? So clearly, instead of probability, you have odds and log odds, and relationship between them and x is much more intuitive, intuitive and easy to understand. For example, if you increase x, if you increase x by regular intervals of say 11.5, how will that affect the log odds? Right? You have to find this. Suppose if you increase x by the regular interval of say 11.5, what how it will affect your log odds? Now we'll try to play with the log odds. So I just have done this calculation. You can try to do that. So probability and odds. If probability is 0, odds will be 0. If probability is 0.25, odds will be 0.33. If probability is 0.4, odds will be 0.67. If probability P is equals to 0.6, it will be 1.5. If odds is 3, probability is 0.75. And if it is 1, it will be infinity. Right? So you can try to do this and find the relation between them. Now, what we can do is, now this is very theoretical, but I like to mention log odds point, right? If we, yeah, okay. So depending upon my, suppose I have this data of blood sugar level, I have probability, I have odds, and I have log odds, right? And I've done calculation for this. Let's say probability if blood sugar level is 129, probability is 0.005, odds is 0.005, log odds is minus 5.30. This is minus 4.51. Here it is 141. So I'm just taking from that data. You can try to do that. If it is 160, it is 0.034, 0.036, and this is minus 3.32, and so on, right? You can do, and we can do calculation, and we can easily plot the graph between log odds on the y-axis and blood sugar level on the x-axis, right? You can try to find a graph. Here it will be 0x, suppose. So it comes like this. The graph will come like this. Now, when it comes to your log odds ratio, if you increase your x value, right? Now, what I'm trying to do is, suppose my blood sugar level is 220, my log odds ratio is, my odds ratio is 0.74. And I'm trying to add this with 11.5. I'm just increasing my x value, that is blood sugar level, with your 11.5. So it will be 231.5. And you'll surprised to see that your odds ratio will become double, right? Again, you try to add this with 11.5. Let's say it becomes 243. Again, it will be somewhat double. You try to do that. It will be 2.94, right? And again, if you add 11.5, it will be double. So if you observe this pattern, if you add 11.5 to your blood sugar level, your uh, what we can say, yeah, your odds ratio is getting double, right? So that's what it is. Now, if you just add again 11.5, it will be double. 2.94 will get double. So for this example, if I just add 244, it becomes 254.5. It becomes approximately double. That will be 5.9. And that's what it is. So that is your pattern. Relationship between X and probability is not intuitive, while that's between X and log odds and odds is, that is intuitive. So this is important. This has important implications. Suppose you are discussing blood sugar levels and the probability that they are corresponds to. While talking about four patients with sugar level 180, 200, 220, 240, you'll not be able to intuitively understand the relation between their probabilities, right? However, if you're talking about the log odds of these four patients, you know that their log odds are in a linearly increasing pattern. They are in a linearly increasing pattern as I've drawn over here. So, and that odds are also multiplicatively increasing pattern, that is 0.1, 0.4, 1.4, and like that, with the increasing by a factor of 3.55. So hence many times it makes more sense to present logistic regression model results in terms of log odds or odds than to talk about in terms of probability. And this happens especially uh, a lot in the industry like finance, banking, and etc. So that's the end of this discussion of univariate logistic regression. You studied logistic regression is, you studied specifically what sigmoid function is, which has equation p is equals to 1 divided by 1 plus e to the power minus beta 0 plus beta 1 x. However, this is not the only form of logistic regression. We have learned the other forms as well, right? But as our syllabus and everything is concerned, you don't need to go beyond this. If you wish to learn, I'll provide links for that. There are different forms of logistic regression, and that is some statistical part, mathematical part. You don't need to worry about that. For this course, you don't need to know about the other forms of logistic regression, right? So that's what the scenario is. I have not written down the notes for this discussion. You can go and watch this recording and try to add notes by your own for this last part, right? The same only, like relationship between X and probability is not intuitive, but between X and odds, log odds is. So this has very important implications, right? So we'll do that. I mean, you can try to write down the notes for that. All right. Now we will try to do multivariate logistic regression. So this was only single or univariate, means we have only one, uh, what we can say, independent variable, right? So the equation was p is equals to 1 divided by 1 plus e to the power minus beta 0 plus beta 1 x, this way. So above variable can have only one x, right? But when it comes to multiple logistic regression, multivariate analysis, your probability will become 1 divided by 1 plus e to the power minus beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus so on up to beta n xn, right? That is what it is. Now we will actually now in this session of multivariate logistic regression, multivariate logistic regression, we are going to build a multivariate logistic regression model in Python. Will conduct feature selection for logistic regression using automated methods, that is RFE, that is recursive feature elimination, manual method, that is VIF, and p-value check. We'll use a dataset in this session to build a model using multivariate logistic regression. And in that, we are going to perform several steps like data cleaning and preparation. We'll pre-process different steps, pre-processing steps, basically. Then we'll see test trend splits, feature scaling if it is required. And last but not the least, model building using RFE, probability values, and VIFs. Apart from the familiar old steps, you'll also be introduced to something known as confusion matrix. And you'll also learn how the accuracy is measured using accuracy is measured for a logistic regression model. All right, so let us try to build a model. So I'll just share a dataset with you. Today is day 21 and it's being 15th December. Multivariate logistic regression. Multivariate logistic regression. And we'll try to, I'll just share a dataset with you. So we have four dataset here. First one is churn data, churn, this one. Second one is internet data. Third one is customer data, this one. Fourth one is data dictionary. No, that is fine. We have only three data. Three data, okay. And we'll create a Colab notebook here itself. And let's rename this as multivariate logistic regression. right? Even though it has regression name in that particular machine learning model, but it is not a regression. It is a classification model, right? Okay. Now I think we can we are ready to go with the practical part. I'll just upload this data. This is our data. The data is internet data, churn data, and third was customer data. Customer data. Okay. All right. Now, if you find the first five records of all this data, the customer ID is common between them. So that's why we can easily merge that, right? So I'll write on telecom churn case study. We have 21 predictor variable over here. 21. We need to predict whether a particular customer will switch to another telecom provider or not. In telecom terminology, this is referred to as churning and not churning, respectively. Right? So I'm going to suppress the warnings, import warnings, warnings dot filtered warnings, in quotes, ignore. And I'm going to import the necessary libraries, importing pandas as PD, import numpy as np, churn underscore data is equals to PD dot read underscore CSV, churn data dot CSV. So I'll just copy this path, I'll paste it over here. Then if you just check the head of this data, so this is our data, right? Then we'll just load customer underscore data is equals to PD dot read underscore CSV, customer underscore data, this one, copy path, paste it over here, customer underscore data dot head, open and close bracket. Then we have internet underscore data is equals to PD dot read underscore CSV, and this is our internet data. This one, we'll copy this, we'll paste it over here, internet underscore data dot head, open and close bracket, right? And if you see, all of this data has first five records common. So customer ID is common. 7590, 7590, 9237, 9237, and 9237. Same, right? So it means customer ID is common and we can combine all this data, all data files into one consolidated data frame. So I'm going to merge on customer ID column df underscore 1 is equals to pd dot merge. I'm going to merge which data? Churn data, customer data. I'll do inner join. How is equals to inner. And on which data? On which column? Customer ID column, because that is your common column. Right? Now final data frame with all predictor variables is telecom. Let's rename that to telecom. pd dot merge df underscore 1 internet underscore data is equals to inner on is equals to customer ID column. And I'm going to write on step 2, which is exactly equals to inspecting the data frame. That is, let's see the head of our master data set. Write on telecom dot head. Open and close bracket. So that is your data. Now let us check the dimensions of the data frame. Let us check the dimensions of the data frame. So we'll write down telecom dot shape. Telecom dot shape. Right? And let's look at the statistical aspects of the data frame. That is telecom dot describe. Open and close bracket. So this is statistical aspects of the data frame, right? Now we can see type of each column. We can write down, let's see the type of each column. Telecom dot info. Open and close bracket. So the data type of these columns are, you can find this. Now let's try to prepare the data. Like we need to do the encoding, right? Because if you see, most of the columns are not numerical. That is phone service, paperless billing, churn, partner, and dependents. These are the non-numeric data, right? So uh, what we'll do is we can easily map this, right? By using map function. So let's try to write down that. My step 3 is data preparation. I'm going to convert some binary variables, that is yes, no, to zeros or one. And I'm going to list all the variables to map. I'll write on variable list is equals to phone, service, comma, paperless billing, comma, we have churn, comma, we have partner, right? We have dependents. And we are going to define the map function. So let's define binary map function. In that we can pass x. We can return x dot map. Whether it is yes, it should be 1. And if it is no, it should be 0. Right? And we are going to apply these functions to all the variables, that is telecom var list. In this telecom data set, on this variables, that is this variable list, we are going to apply this binary map function. So yes will be replaced with 1, no will be replaced with 0. If you do this, you'll get the output. And if you just try to see telecom.head, open and close bracket, you can get the, you can see that phone service, paperless billing, churn is easily encoded, right? And other columns. Now, for categorical variables with multiple levels, we are going to create a dummy features, that is one hot encoded features. I'm going to create a dummy variable for some of the categorical variables and dropping the first one. Dummy1 is equals to pd dot get underscore dummies telecom contract payment method, comma, gender. Then we have internet services as well, right? So for this variable, we are going to create a dummy variable, which is your one hot encoding, right? So internet service, comma, drop underscore first is equals to true. And I'm going to add the results to the master data frame. So I'll write on telecom is equals to pd dot concat. And whatever I have, that is my telecom data frame. I want to add that with with the dummy variable one, which I have created over here, right? And I can write an access equals to 1 because I want to do the column wise addition of the data. Now I think it is done. If you just check telecom.head, you'll be able to get this output. This is my data, right? Now I'm going to create dummy variables for the remaining categorical variables and dropping the level with beginnings. So creating dummy variables for the variable multiple lines, and I'll write an M1 or ML is equals to multiple lines, right? So pd dot get underscore dummies telecom of multiple lines, prefix is equals to multiple lines. So for this multiple lines data, uh, now we'll check ML, what is there in ML, ML dot head. So this multiple lines is successfully converted into dummy variables. Now we need to drop one variable, that is drop first is equals to true. So we can give heading as dropping the dropping multiple lines, no phone, service, column. So we'll write down ML1 is equals to ML dot drop. We are going to drop multiple lines phone service because any one column is fine. So I want to drop this and I'm going to concat my telecom with ML1. So in multiple lines, I only have this two multiple lines no and multiple lines yes because this is redundant as we have discussed. This is redundant. Any one column is redundant. So you can drop any one and we can add that to our telecom data. If I run this, I'll be able to get the okay. X 1 to 2 positional arguments, but three were given. Where these are three. Service. Hmm. Now, once this is added, we can check telecom dot head. So if you see multiple lines, variable is added at the end, right? Now, same for online security column. We need to do that. Online security, we have, where is online security? If you just write down info, you'll get all the list of the columns out there, right? Then you'll be able to see this online security. Online security, online backup, then device protection, tech support, streaming TV, and streaming movies. This column, we have to do the encoding for that, right? So if you just see telecom, double square bracket, uh, online security, comma, online backup, comma, device protection, comma, tech support, comma, streaming TV, comma, streaming movies, right? And if you just check this, for this column itself, you have to do encoding, right? We have yes and no, and pd.getDummies is the solution for that. So let us try to do this. I'll do it in the one line itself so that you guys get an idea about that. We are going to do the same step which we have followed over here, dropping this. Uh, Initially doing get dummies, then dropping any one column out there and adding and concat this to your original data, right? For all these columns out there. So first step is uh, creating dummy variables for the variable online security. We'll write down OS is equals to pd.get underscore dummies telecom online security, comma, prefix is equals to online security We are going to create, uh, yeah, we need to drop this, right? We'll write an OS1 is equals to os.drop online security underscore no underscore internet service, comma access is equals to 1, adding the results to the master data frame, telecom is equals to pd.concat telecom, comma os1, comma access is equals to 1. Now creating dummy variables for the variable online backup. So OB is equals to pd.get underscore dummies telecom online backup, comma prefix is equals to online backup. OB1 is equals to ob.drop online backup underscore no internet service, comma 1. Then I'm going to add the results to the master data frame. Telecom is equals to pd.concat telecom, comma ob1, comma access is equals to 1. Then I'm going to create dummy variables for variable tech support. ES is equals to pd.get underscore dummies telecom tech support, comma prefix is equals to tech support. Online backup done. Device protection is remaining. No tech support and okay. After tech support, we'll do that. TS1 is equals to drop internet service. Device protection is remaining. But before that, we'll add this to master data frame. Telecom is equals to pd.concat. I want to concat telecom, comma TS1, comma access is equals to 1. Then I'm going to create a dummy variable for device protection. DP is equals to pd.get underscore dummies telecom device protection, comma prefix is equals to device protection. DP1 is equals to dp.drop device protection underscore no internet service, comma access is equals to 1. Should be also access is equals to 1, and this should also be access is equals to 1. So how many columns do we have earlier here? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4. Adding the results to the master data frame. Adding the results to master data frame. So uh, telecom.pd concat dp1. Yes. So dp1 is done. Now two columns are remaining, that is streaming TV and streaming movies. So create dummy variable for the streaming TV column. St is equals to pd dot get underscore dummies for streaming TV. We are going to drop this, adding to the data frame, add this, and we are going to create dummy variables for the variable streaming movies. So sm is equals to pd dot get underscore dummies telecom streaming movies, prefix equals to streaming movies. Drop and adding this to the master data. Transportation, no internet service is not found in the axis. Okay. Device protection spelling, is it wrong? Protection. Service spelling is wrong. Service. Now it is done. And now it's time to check the head of the data. The data preparation is done. We want to drop the repeated variables. So if you see in this data, we have some repeated variables like we have contract, we have payment method, we have gender, and we have multiple lines internet service, because that is repeated, right? We have done encoding for that already. So we'll just remove that. That is a repeated variables. So I can put heading as dropping the repeated variables. So I can write on, we have created dummies for the below variables. So we can drop them easily. So telecom is equals to telecom dot drop, and these are the contract payment method, gender, multiple lines. These are the variables that we are going to drop, because that is repeated. We have numerical variables for that. We have categorical variables for that. So we are removing categorical variables because we already have done pd dot get dummies. So there is no need to have any categorical variables. And the variable that was imported as a string, we need to convert it to float. So I'm going to write on telecom is equals telecom of total charges equal to telecom of total charges dot convert into objects. So converting the total charges column, sorry, convert objects, telecom, total charges. Series attribute has no attribute convert objects. Let us try to do this in Jupyter Notebook, because whatever we have written is correct and valid. But this is, I think this is your bug for Jupyter Colab. So let us try to do the same thing in Colab, not Colab, Jupyter Notebook. I'll just share my screen. We can create new folder. We can rename this as multivariate logistic regression. And we'll just upload the data over here. So churn data, internet data, and customer data. And let us upload that file. Let us restart and run all this. Yeah, one more thing. This should not be content. This should be only churn data. Same goes with this customer data. And this should be internet data, not content. Yeah, now if I restart and run all this, okay. So again, here also we don't have convert objects. It was there earlier because I have done this few years back. Anyway, let us keep that then. Telecom dot info, open and close bracket. Now we are going to check for outliers. So anyway, here only we can do that because you guys will get this automatically on your drive, telecom.info. Now we are going to have a check for outliers. Checking for outlier in the continuous variables. So numerical underscore telecom is equals to telecom tenure, comma, monthly charges, comma, senior citizen, comma, total charges. And I'm going to have a check for outliers at 25%, 50%, 75%, 90%, 95%, and 99%. Right? So I'll run numerical underscore telecom dot describe percentile is equals to 0.25, comma, 0.5, comma, 0.75, comma, 0.90, comma, 0.95, comma, 0.99. So these are the percentile that we are getting. And from the distribution above, you can see that there are no outliers in the data because you just need to compare the ranges. Here we have 9. Screen share is not showing. Okay. Yeah. So so we are actually just having a look at the percentiles over here. These are the percentiles, right? And from the percentiles itself, from the percentage itself, from the range itself, were we are getting the idea about the outliers. I'll just show you this point. Um, Before that, we can have a break for 5 minutes. And in this break, you guys will be having a quiz now.
Yeah, thank you. I have shared the link in chat box. Kindly join. Only 6 members has joined. Others, please join fast.
Yes. So think we can start with the next part. Hmm. So we are going to write down the analysis for this. We are going to write down from the distribution shown above. You can see that there are no outliers in your data, and the numbers are gradually increasing. So we are going to check for missing values and impute them. We're going to add up the missing values, that is column wise, let on telecom dot is null dot sum. So it means that, okay, do we have any null values? We do not have any null values. Monthly charges also don't have null values. Okay, that's good. So in total charges column, do we have null values? Don't have null values. Perfect. So I think we can directly move with the model building now, which is train test split. Train test split. That is just step number 4. So we'll write down from sklearn dot model underscore selection. We're going to import train underscore test underscore split. And we are putting feature variable to x, that is capital X is equals to telecom dot drop. We are going to drop churn and customer ID, comma access is equals to 1, x dot head. So putting response variable to y, that is y is equals to telecom of churn. And because you already know in y what do you have? You have the target variable. That is a response variable. So we'll check y dot head. And then we are going to split our data into, sorry, telecom, not tech support, it is churn. Now we are going to split our data into train and test. X underscore train, comma x underscore test, comma y underscore train, comma y underscore test is equals to train test split x comma y comma train underscore size is equals to 0.7 comma test underscore size is equals to 0.3 comma random underscore state is equals to 100. Step 5 is feature scaling. So from sklearn dot pre-processing, we are going to import standard scalar. Scalar is equals to standard scalar, open and close bracket, capital X underscore train, tenure, comma, monthly charges, comma, total charges is equals to scalar dot fit underscore transform X underscore train of tenure, comma, monthly charges, comma, total charges. And we're going to write an X underscore train dot head. Would not convert string to float. Monthly charges are not in index. Oh, M is capital. Okay, monthly charges is it a string? Yeah, I think it's a string. That's the reason we are trying to convert that into numeric format, right? By using AS type. So if you just see, earlier we were getting error for those line where we were not able to convert this into string, right? See, this is what I'm talking about. Here itself, I was trying to convert this objects into numeric, but it was not happening because if you see, this should not be object, monthly charges. Or is it float only? Why we are not able to convert this into, okay, let us try it one more time. Scalar is equals to standard scalar. Close bracket. And we'll write down X underscore train of tenure, comma, monthly charges, comma, total charges is equals to scalar dot fit underscore transform X underscore train of tenure, monthly charges, and total charges. Okay, let's do it one by one then. I want to do it for tenure. Uh, Here also I'll do it for tenure. Expect a two-dimensional container, but class got series instead. Press a data frame, pass a data frame in a single. Okay. Here also we should pass this. Hmm. So tenure is fine. Now, same thing I am interested to do it for other column. That is same thing I'm interested to do it for other columns. That is your uh, monthly charges, capital M, monthly charges. And here also it should be same. Copy this and I'm going to paste it over here. And I'll do it for the other column, that is your total charges. So for total charges itself, it was having a problem. It says it is a string. We cannot convert that to float. Total charges. So in this telecom dot या फिर in this x underscore train, I'll just check data type of the total charges. It is object. We need to convert that into float. Now, how can you do that is we have one method which is known as as type. We'll see that as type to float. So we just need to write down pd.to numeric. This is fine. Or else this one. Yes. So this of that column dot as dot float. So I just need to convert monthly charges, not monthly charges, total charges, no? Total charges to float. So df of total underscore charges. They should be x underscore train is equals to x underscore train of total charges as float. Columns, none of the index total charges. Acha, this is your, so no underscore. Could not convert string to float. Okay. I'm not understanding why it is not converting. Anyway, we'll see this in the next session. We just need to convert this into float. Even if you don't do that, that is also fine. We'll just get little less accuracy. So it means that we are not scaling that particular data, which is your uh, total charges, right? That is object. We need to convert that to float. That's why the thing is happening. Let's do one last try. One last try for total charges, which is telecom of total charges column. I want to convert this to, yeah, it's happening now. Okay. Now I think we can do this for total charges over here. So here it should be total charges. Control C, Control V, C, Control V. Again, to not convert. We are converting this into numeric, right? So ideally it should be numeric. The data type should be numeric for total charges. Yeah, it's float only, no? Okay, okay. But extrain, uh, in extrain itself, it is not changed. So in extrain we can change. Okay, let's do this. Same thing, we can do it for. Okay, if I just restart and run all this, then it will happen, yes. Because the sequence is not proper. What we'll do is I'll just do this for total charges column. here. It will happen, yes. Let's hope for that. Now it will not happen, but if I just restart and run all this, it will be every cell will run proper sequence wise. So that there might be chance of, yeah, this should be before xtrend, before doing trend test split. Wherever we were getting error, I think it was dropping the related variables. Yeah, before doing trend test split, we should add this because after trend test split, we are converting that to numeric, right? But so yeah, can you see this? Now it's happening. Now the last part, I think we already have done the scaling. It's already in a single range. You can check x underscore train uh, dot head to just get an idea about if all the data is in a single range or not. So it is there, right? Zero and in between zeros and one or minus one to one. And now all is good. We are good to go with the model building part. We'll look at the correlation and just have a look at the multicollinearity. That will do it in the next session. So if you guys have got an idea about why I told that it takes 80% of the time to just clean and prepare the data, right? We spend 80 more than 80% of the time to just clean and prepare the data for your model building, right? So there are n number of things that happens. These are one of them. So we just prepare data by doing mapping, encoding is there, scaling is there, to remove outliers is there, n number of tasks are there, right? So that is what we have. We can stop here for the day if you don't have any questions. I already have given this on your drive. You can just have a look at that. This is your drive, right? Chalo. All right then. Thank you. Happy learning. Bye.
People?
Yes.
Yeah, one second. One second. It's a connection. If I don't know how to connect the Python to SQL. Can you
Sorry.
be a Python? How to install? Sorry, in my SQL connected. I don't know how to connect it.
Could you please repeat? Your voice is very less. Very.
Now it's cold. That's why it's now you hearing my voice.
Yeah, yeah, yeah.
Yeah, I need to connect Jupyter Notebook to MySQL, but I don't know how to connect it. If I connect it, can I share my screen? I am already asking this doubt. Later, I just need to look on your record, but I didn't get it how to connect it. Can I share?
Um, can we just do it in the next session because it's already
Uh,
8.
Please, people, they're giving assignment. I'm already asking, but you saying next section. That's it.
You could have asked it earlier, no? Because we already
Yeah,
have
yeah. I'm
research.
already asking you. Said next time we can. You
No, no.
say
What I'm saying is it's already 11:30, right?
okay. Now I don't know how it connected because today is the deadline assignment submission. That's why I'm asking to you.
Yes. See, these technical related issues and everything like that you are facing related to errors or anything like that, you should ask this to your. There is separate team for Gooby, right? Which will help you out for the technical part. Apart from trainers, I think
Okay.
you guys have another mentor from the internal team. You can
Okay.
call them and you can resolve this type of issues, right?
Okay.
I'll just let them know. You can connect with them.
Okay.
Uh, Either you can connect with your coordinators or you can connect with the internal team member. In
Okay.
the last session, I think somebody has joined for explaining the assignments, right? You can contact
Yes.
that.
Yeah. Okay.
Okay, thank you. Yes, Darshini, I'm preparing that bike sharing assignment. You guys will be getting it on your drive by today, end of the day, right? So here itself, you will get this. Everything is ready. Only thing is I just need to modify and edit that PDF in which we have questions, right? So we'll do that. Don't worry. All right. All right then, everyone. Thank you. Happy learning. And just one more last point. You guys need to revise this continuously because things are getting complicated, you can say, or advanced from now onwards, right? So if you're not revising this, you'll not be able to recollect and understand what we are doing. Chalo. Thank you, everyone. Bye.